Close your eyes, and let's journey back through time, to a moment when our galaxy didn't yet exist. Before the stars, before the planets, before everything familiar, there was only darkness and potential. Our story begins 13.6 billion years ago, shortly after the Big Bang itself. In the cooling aftermath of creation, the universe was a vast sea of hydrogen and helium, the two simplest elements, drifting through the cosmic void. For millions of years, this primordial soup expanded and cooled in silence. No light. No sound. Just gravity, quietly pulling at these clouds of gas, drawing them together in invisible patterns that would one day become galaxies. Around 13 billion years ago, the first stirrings of what would become our Milky Way galaxy began to take shape. Small protogalactic clouds, each containing millions of times the mass of our Sun, started colliding and merging together in a slow, elegant dance that would last for eons. Imagine it, fragments scattered across hundreds of thousands of light years, gradually falling together under gravity's patient hand, like raindrops gathering into streams, streams into rivers. These early building blocks weren't forming alone. Our galaxy was born as part of a larger cosmic web, with dark matter providing the invisible scaffolding. This mysterious substance, which makes up about 85% of all matter in the universe, created gravitational wells where normal matter could collect and condense. Like a spider's web glistening with morning dew, the dark matter framework caught clouds of gas, guiding them into the spiral shape we would one day recognize as home. As these gas clouds continued to collapse under their own gravity, something remarkable happened. Roughly 12 to 13 billion years ago, the very first stars in our galaxy ignited. These weren't stars like our Sun. They were enormous, brilliant giants, hundreds of times more massive, burning with fierce intensity. These ancient suns lived fast and died young, existing for only a few million years before exploding in spectacular supernovae. But their brief lives were not in vain. When these first-generation stars exploded, they seeded the galaxy with new elements. Inside their nuclear furnaces and in the final explosive moments of their deaths, they forged carbon, oxygen, iron, and all the heavier elements that would eventually make planets, and life itself, possible. Each supernova scattered these treasures across thousands of light years, enriching the cosmic clouds, adding complexity to what had been only hydrogen and helium. Over billions of years, our galaxy continued to grow through cosmic collisions. The Milky Way as we know it today is actually the product of numerous mergers with smaller dwarf galaxies. Each collision added new stars, new gas clouds, new possibilities to the growing spiral structure. Even now, this process continues. Like a river accepting tributaries, our galaxy slowly consumes smaller neighbors, weaving their stars into our own. Around 10 billion years ago, the Milky Way's distinctive spiral arms began to form. These aren't solid structures but rather density waves, regions where stars and gas bunch together temporarily as they orbit the galactic center, like traffic slowing on a cosmic highway. The spiral pattern emerged from the physics of rotation, as the galaxy spun, faster near the center and slower at the edges. Matter organized itself into these elegant, sweeping curves. At the heart of this growing spiral, something dark and powerful was taking shape. A supermassive black hole, eventually growing to more than 4 million times the mass of our Sun, settled at the galactic center. We call it Sagittarius A star, and it acts as the gravitational anchor around which hundreds of billions of stars orbit. This central black hole didn't form all at once. It grew slowly, patiently, accreting matter over billions of years, pulling in gas and dust and occasional unlucky stars that wandered too close. By about 8 billion years ago, the basic structure of our modern Milky Way was in place. The galaxy had settled into a rotating disk about 100,000 light-years across, with spiral arms wound through it, a bright central bulge, and a spherical halo of ancient stars surrounding everything like a whisper of its earliest days. And there, in this vast cosmic wheel, with trillions upon trillions of stars yet to be born, the stage was set for our own chapter of the story, still billions of years in the future. But that is a tale for the next part of our journey. For now, rest in this ancient darkness, in the knowledge that our galaxy has been slowly, patiently building toward this moment, for nearly 14 billion years. We've watched our galaxy take its first shape, seen its spiral arms unfurl across the cosmic dark. Now, let's drift forward through time, to an era of incredible creativity and transformation, when the Milky Way became a stellar nursery on an unimaginable scale. Between 10 and 8 billion years ago, our galaxy entered its most prolific period of star formation. During this cosmic baby boom, new stars were being born at a rate nearly 10 times faster than today, with massive clouds of gas and dust collapsing to create millions upon millions of new suns across the galactic disk. The galaxy glowed with the light of youth, brilliant and bright, as generation after generation of stars ignited in the darkness. Within these star-forming regions, something remarkable was happening in the physics of creation itself. Stars don't form alone, they're born in clusters, sometimes hundreds or thousands at a time, all emerging from the same giant molecular cloud. These stellar siblings would eventually drift apart over millions of years, scattered by the galaxy's rotation and their own gravitational interactions. Our own sun was born this way, in a cluster of sibling stars we'll never know, now separated by vast distances across the galaxy. Around 6 billion years ago, the Milky Way experienced a dramatic event, a major collision with another galaxy. This wasn't a gentle merger but a significant disruption that sent shockwaves through the galactic disk, triggering new bursts of star formation and reshaping portions of the spiral structure. The evidence of this ancient collision still exists today, written in the unusual motions of certain star groups, like ripples frozen in time. It was during this era, roughly 4.6 billion years ago, that our own solar system was born. In a quiet corner of one of the galaxy's spiral arms, about 26,000 light-years from the galactic center, a cloud of gas and dust began to collapse. Within this cloud, our sun ignited, and around it, the planets began to form from the leftover material. We are children of this moment, cosmic dust that learned to contemplate the stars. The location of our solar system within the galaxy isn't random, it's actually quite fortunate. We orbit in what astronomers call the galactic habitable zone, a region neither too close to the violent galactic center nor too far out in the sparse outer reaches. Here, there's enough heavy elements to form rocky planets, but not so much stellar activity that life would be constantly threatened by radiation or gravitational disruptions. We circle the galaxy at a stately pace, taking about 225 to 250 million years to complete one full orbit, a cosmic year. As our solar system was forming, the Milky Way contained approximately 200 billion stars, though this number has grown since. Each one is a sun, many with their own families of planets, and scattered throughout the galactic disk like grains of sand on an endless beach. If you could see all these stars at once, from outside the galaxy, you'd witness a grand spiral of light, but from within, from our perspective, we see only the narrow band of the Milky Way stretching across our night sky. The spiral arms where most star formation occurs aren't actually fixed structures that rotate with the galaxy. Instead, they're density waves, regions where stars and gas temporarily bunch together as they orbit at different speeds. Think of it like a traffic jam on a highway. The cars move through it, but the jam itself stays in roughly the same place. This means our solar system drifts in and out of spiral arms over the course of its orbit, spending about 10 million years crossing through each arm's increased stellar density. Throughout this age of formation, globular clusters, dense spherical collections of hundreds of thousands of ancient stars, continued to orbit the galaxy in a vast halo. These clusters, some of the oldest objects in the Milky Way, formed in the earliest days and survived every collision, every merger, every transformation the galaxy underwent. They orbit like distant moons around a planet, taking hundreds of millions of years to complete their eccentric paths, witnesses to everything our galaxy has become. And so the Milky Way matured, its structure established, its rhythms set, its countless stars burning through their life cycles. Birth and death, creation and destruction, all woven into the grand tapestry of galactic time. Rest now in this knowledge, that our galaxy has been preparing for this moment, creating and recreating itself, for billions of years before we arrived. Our galaxy is not a static museum piece, frozen in time. It breathes, it moves, it changes. Let's explore the Milky Way as a living system, dynamic, evolving, and full of hidden wonders that reveal themselves only to patient observation. The entire galaxy rotates, but not like a solid wheel. Different parts spin at different speeds in what astronomers call differential rotation. Near the center, stars complete their orbits in just a few million years, while out in the distant reaches, where our solar system resides, it takes hundreds of millions of years to make one complete journey around the galactic core. This differential rotation is what maintains the spiral arms, like cream stirred into coffee, creating these elegant, swirling patterns that never quite mix completely. Between the stars lies something just as important as the stars themselves, the interstellar medium. This thin gas and dust, spread across vast distances, makes up about 10 to 15% of the visible matter in our galaxy. Though it seems empty, this is where new stars are born, and it's enriched continuously by the deaths of old stars. In some places, the interstellar medium is so tenuous that there are only a few atoms per cubic centimeter, yet across the galaxy's vast volume, this adds up to billions of solar masses of material. Our galaxy contains enormous structures called stellar streams, long ribbons of stars that trace the orbits of smaller galaxies that the Milky Way has consumed over billions of years. These streams can stretch for hundreds of thousands of light years, like cosmic breadcrumb trails marking the paths of galaxies that no longer exist as separate entities. The Sagittarius stream is one of the most prominent, wrapping around our galaxy multiple times as the remnant Sagittarius dwarf galaxy slowly gets torn apart by the Milky Way's gravity. Deep within the densest molecular clouds, where gas and dust block out all starlight, the temperature drops to just 10 to 20 degrees above absolute zero. In this profound cold and darkness, complex organic molecules form, including amino acids and sugars, the building blocks of life. These molecules are found throughout the galaxy, suggesting that the ingredients for life are common in the universe. Star formation happens in these cold, dark places, where gravity can finally overcome the pressure of gas, allowing clouds to collapse. The Milky Way's disk isn't perfectly flat, it's warped, like the brim of a hat that's been sat on. This warping becomes more pronounced toward the outer edges and is likely caused by gravitational interactions with satellite galaxies, particularly the Large and Small Magellanic Clouds. The disk ripples up and down by thousands of light years in these outer regions. From our position inside, we can't easily see this warping, but by mapping the positions of distant stars and gas clouds, astronomers have revealed the galaxy's subtle, three-dimensional shape. Throughout the galactic disk, there are vast bubbles and cavities blown out by supernovae and the powerful winds from massive stars. These bubbles can be hundreds of light years across, creating regions where the interstellar medium is pushed aside, leaving hot, thin gas in their wake. When multiple supernovae explode in the same region, they can create superbubbles that break through the galactic disk entirely. Our own solar system currently resides within one such structure, the local bubble, a cavity about 1,000 light years across, created by supernovae that exploded millions of years ago. The galaxy contains mysterious dark matter, which we cannot see directly but whose presence we can infer from its gravitational effects. This invisible matter makes up about 85% of the total mass in the galaxy, forming an enormous halo that extends far beyond the visible stars. Without dark matter's gravitational embrace, the galaxy would spin apart. The stars in the outer regions are moving too fast to be held by the gravity of visible matter alone. We swim through this dark matter constantly, though it interacts with ordinary matter only through gravity, passing through us like cosmic ghosts. At this very moment, our galaxy is on a collision course with our nearest large galactic neighbor, Andromeda. The two galaxies are approaching each other at about 110 kilometers per second, and in approximately 4 to 5 billion years, they will begin to merge. This won't be a violent collision. Stars are so far apart that they'll mostly pass by each other like dancers in a cosmic ballet. But the gravitational interactions will be spectacular, reshaping both galaxies over hundreds of millions of years, eventually forming a single, larger elliptical galaxy that astronomers have playfully nicknamed Milkomeda. The Milky Way continues its ancient dance, rotating, evolving, consuming smaller galaxies while preparing for its eventual merger with Andromeda. All of this happens on timescales so vast that to our brief human lives, the galaxy seems eternal and unchanging. Yet it flows like water, like time itself, patient and inexorable. Rest in this cosmic current, knowing that you are part of this great galactic river, flowing through space and time. Let's turn our attention now to the grand architecture of our galaxy, the structures that shape it, the forces that govern it, and the different neighborhoods that make up this vast cosmic city we call home. The Milky Way is classified as a barred spiral galaxy, meaning it has a central bar-shaped structure made of stars that extends from the galactic core. This bar is about 27,000 light-years long and acts like a cosmic highway, funneling gas from the outer disk toward the center, feeding star formation and the central black hole. The bar rotates more slowly than the disk around it, creating a complex gravitational dance that helps maintain the galaxy's structure over billions of years. Our galaxy has 4 major spiral arms: the Perseus arm, the Scutum Centaurus arm, the Norma arm, and the Sagittarius arm. Our solar system doesn't reside in any of these major arms but rather in a smaller structure called the Orion Spur, or the Orion Arm, a minor branch that connects the Perseus and Sagittarius arms. Think of it as living on a quiet side street off a major boulevard, less stellar traffic, more peaceful, perhaps more conducive to the long-term stability needed for life to evolve. The galactic center is one of the most extreme environments in the Milky Way. Within just a few light-years of Sagittarius A star, the supermassive black hole, stars orbit at incredible speeds, some completing an orbit in just a few years, traveling at several % of the speed of light. The star known as S2 completes its elliptical orbit around the black hole in just 16 years, providing scientists with a natural laboratory for testing Einstein's theories of gravity. This central region is so crowded with stars that if we lived there, our night sky would contain thousands of stars brighter than Sirius, the brightest star in our current sky. Surrounding the galactic disk is the galactic bulge, a dense, roughly spherical concentration of mostly older stars. This bulge contains about 10 billion solar masses worth of stars packed into a region just a few thousand light-years across. The stars here are older, redder, and formed primarily in the galaxy's early history. The bulge glows with a warm, golden light, the combined glow of billions of ancient suns, like embers in a cosmic hearth. Beyond the visible disk and bulge lies the galactic halo, a vast spherical region extending perhaps 600,000 light-years from the galactic center. Here, the globular clusters orbit in their eccentric paths, along with individual halo stars and streams from destroyed dwarf galaxies. The halo is also where most of the galaxy's dark matter resides. This outer realm is sparse and quiet, a cosmic wilderness compared to the bustling stellar cities of the disk. Throughout the galaxy, there are regions called HII regions, vast clouds of ionized hydrogen gas lit up by the intense ultraviolet radiation from young, massive stars. These stellar nurseries glow with characteristic red and pink hues and can stretch across hundreds of light-years. The Orion Nebula, visible to the naked eye, is one such region, a stellar nursery just 1,500 light-years away where new stars are being born right now. If you could see in infrared light, these regions would reveal hundreds or thousands of infant stars still hidden within their dusty cocoons. The Milky Way contains different populations of stars that tell the story of its evolution. Population 1 stars, like our Sun, are relatively young and metal-rich, found primarily in the disk and spiral arms. Population 2 stars are older, formed in the galaxy's early days, and contain fewer heavy elements. They populate the bulge and halo. Some astronomers also refer to an even older population 3, the very first stars in the universe, made purely of hydrogen and helium, though none have been directly observed in our galaxy. Each population is like a chapter in the galaxy's autobiography, written in starlight. The galaxy's magnetic field threads through the entire structure, following the spiral arms and extending into the halo. This field is weak by terrestrial standards, about 1,000,000 times weaker than Earth's magnetic field, but across the vast scales of the galaxy, it plays a crucial role in shaping the interstellar medium, guiding cosmic rays, and influencing star formation. The magnetic field lines spiral around the galaxy like invisible threads, weaving together the fabric of galactic space. These structures, the bar, the arms, the bulge, the halo, are not separate pieces but parts of an integrated whole. They work together, influence each other, creating the complex, beautiful system we observe. The galaxy is architecture on a cosmic scale, not built by hands, but by gravity, time, and the physics of matter and energy playing out across billions of years. Let yourself drift through these vast spaces, past glowing nebulae, through spiral arms, out into the quiet halo. You are safe here, in this grand design. We've explored the galaxy's structure, its grand architecture. Now let's journey into the lives of its inhabitants, the stars themselves. Each one is born, lives, and dies, contributing to the great cycle that has been repeating for billions of years. Stars in our galaxy come in an extraordinary range of sizes and temperatures. The smallest red dwarf stars can be as little as 8% the mass of our Sun and burn so dimly they could last for trillions of years, far longer than the current age of the universe. The largest stars can be over 100 times the Sun's mass, burning brilliantly but briefly, exhausting their fuel in just a few million years. Between these extremes lies every shade and size imaginable: orange dwarfs, yellow stars like our Sun, white giants, blue supergiants, a spectrum of stellar diversity. The galaxy produces new stars at a rate of about 1 to 3 solar masses per year, a dramatic slowdown from its peak billions of years ago, but still steady creation nonetheless. Most of these new stars are small red dwarfs, which form in far greater numbers than their massive cousins. For every star like our Sun that forms, dozens of smaller red dwarfs ignite. This means the galaxy's population is gradually shifting towards smaller, longer-lived stars, preparing for a distant future when star formation eventually ceases altogether. When a star like our Sun nears the end of its life, it swells into a red giant, expanding to perhaps 100 times its original size. In about 5 billion years, our own Sun will undergo this transformation, its outer layers reaching past Mercury's orbit, possibly even engulfing Venus and Earth. But this isn't the end, it's a transformation. The red giant phase is actually quite beautiful, though brief. The star glows with a deep orange-red light, its outer layers becoming tenuous and translucent, like a cosmic lantern. After the red giant phase, Stars like our Sun shed their outer layers in gentle pulses, creating what astronomers call planetary nebulae, though they have nothing to do with planets. These expanding shells of gas, lit from within by the hot stellar core, create some of the most beautiful structures in the galaxy. They last only tens of thousands of years before dispersing into the interstellar medium, but in that brief moment, they glow with ethereal colors, blues, greens, reds, and purples. The Ring Nebula, the Helix Nebula, the Cat's Eye Nebula, each is the final artwork of a dying sun-like star. What remains after the planetary nebula fades is a white dwarf, a dense, Earth-sized ember containing about half the mass of the original star, compressed to incredible densities. A teaspoon of white dwarf material would weigh several tons. These stellar remnants slowly cool over billions of years, fading from white to yellow to red, and eventually to black dwarfs, though the universe isn't old enough yet for any black dwarfs to exist. Our galaxy contains billions of white dwarfs, the quiet remains of stars that lived and died, still glowing softly in the darkness. Massive stars, those more than 8 times the Sun's mass, meet a far more dramatic end. When they exhaust their nuclear fuel, their cores collapse in a fraction of a second, triggering a supernova explosion so powerful it can briefly outshine the entire galaxy. In that moment, the star releases as much energy as our Sun will produce in its entire 10 billion-year lifetime. These explosions are the primary source of heavy elements in the galaxy: the iron in your blood, the calcium in your bones, the oxygen you breathe. All were forged in the hearts of massive stars and scattered by their deaths. Some supernovae leave behind neutron stars, objects so dense that their protons and electrons have been crushed together to form neutrons. A neutron star packs about 1.5 times the Sun's mass into a sphere just 20 kilometers across. They spin rapidly, sometimes hundreds of times per second, and if their magnetic field is aligned just right, we detect them as pulsars, cosmic lighthouses sweeping beams of radiation across the galaxy. The first pulsar was discovered in 1967 and initially nicknamed LGM-1. Little Green Men 1, because its regular pulses seemed almost artificial. The most massive stars of all, those more than 20 or 30 solar masses, can collapse entirely, forming black holes. These aren't the supermassive black holes at galaxy centers, but stellar mass black holes, typically ranging from a few to a few dozen times the Sun's mass. Our galaxy likely contains hundreds of millions of these stellar black holes, most of them invisible and silent, their presence revealed only when they interact with nearby matter or companion stars. Some of these black holes merge together, creating gravitational waves, ripples in spacetime itself that wash across the galaxy at the speed of light. And so the cycle continues: birth in cold molecular clouds, life burning bright or dim depending on mass, and death in gentle dispersal or violent explosion. Each ending provides the raw materials for new beginnings, enriching the galaxy with the elements needed for planets, for life, for everything we know. The galaxy is a master recycler, wasting nothing, transforming everything. Stars are not permanent, but the matter they're made of is eternal, simply changing form, over and over, through countless generations. Rest now in this eternal cycle, Knowing that the atoms in your body have been through this process many times, forged in stars, scattered by explosions, gathered again into new forms. The Milky Way doesn't exist in isolation. It's part of a cosmic community, surrounded by smaller companion galaxies and embedded in a larger structure that stretches across millions of light years. Let's explore our galactic neighborhood. The Milky Way has dozens of satellite galaxies orbiting it, smaller dwarf galaxies held in gravitational orbit around our larger spiral. The two most prominent are the Large and Small Magellanic Clouds, visible to the naked eye from the southern hemisphere as hazy patches of light. The Large Magellanic Cloud contains about 10 billion stars and orbits about 160,000 light-years away, close enough that it's slowly being distorted by the Milky Way's gravity. These Magellanic Clouds were named by Ferdinand Magellan's crew during their circumnavigation of Earth in the early 1500s, though indigenous peoples of the southern hemisphere had known them for millennia. Many of the Milky Way's dwarf satellite galaxies are incredibly faint, so-called ultra-faint dwarf galaxies that contain only a few thousand stars, making them barely more luminous than a single bright star. Yet they're dominated by dark matter, with some containing 100 times more dark matter than visible matter. These tiny galaxies are important windows into galaxy formation, representing some of the smallest structures that dark matter can hold together. They orbit the Milky Way like moths around a flame, remnants of the galaxy-building era. The Milky Way is the second largest member of what astronomers call the Local Group, a collection of more than 80 galaxies spread across about 10 million light-years. The largest member is the Andromeda Galaxy, which contains about 1 trillion stars, roughly twice as many as the Milky Way. Third in size is the Triangulum Galaxy, a beautiful face-on spiral containing about 40 billion stars. Together, these three spirals dominate the Local Group, with dozens of smaller dwarf galaxies orbiting around them like cosmic families. The space between galaxies in the Local Group isn't completely empty. There are streams of hydrogen gas, stripped from smaller galaxies by gravitational interactions, creating bridges and filaments between the larger structures. The Magellanic Stream, for example, is a ribbon of gas stretching nearly 600,000 light-years across the sky, trailing behind the Magellanic Clouds as they orbit the Milky Way. These gas streams are like cosmic contrails, marking the paths of galaxies through space. About 12 million light-years from us lies the Maffei Group, a collection of galaxies hidden behind the Milky Way's disk. Because these galaxies lie in the zone of avoidance, the region where our own galaxy's gas and dust block our view, they weren't discovered until 1968, when astronomer Paolo Maffei detected them using infrared light that can penetrate the obscuring material. It's humbling to realize that entire galaxies can be hidden from view, concealed behind the veil of our own cosmic home. The Local Group itself is part of an even larger structure called the Virgo supercluster, which contains about 100 galaxy groups and clusters spread across 110 million light-years. At the heart of this supercluster lies the Virgo cluster, containing over 1,000 galaxies. The gravitational pull of this massive cluster affects the motion of the Milky Way and all the galaxies in the Local Group. We're falling toward the Virgo cluster at about 300 kilometers per second, a journey that will take billions of years. Recent mapping of galaxy motions has revealed an even larger structure, the Laniakea supercluster, Hawaiian for immeasurable heaven. This vast cosmic structure contains about 100,000 galaxies, including our own, all sharing common motion through space. The Laniakea supercluster spans 520 million light-years and contains the mass of about 100 quadrillion suns. At the far end of Laniakea lies the Great Attractor, a gravitational anomaly pulling our entire local region of space toward it, though it's partially obscured by the Milky Way itself. Despite being part of these vast structures, the Milky Way and Andromeda are actually moving toward each other faster than the general expansion of the universe would suggest. This is because on local scales, up to a few million light-years, gravity wins over cosmic expansion. The local group is gravitationally bound, meaning its members will never separate due to universal expansion. Instead, they'll continue their slow dance of mutual attraction, eventually merging over billions of years. On the largest scales, galaxy clusters are moving apart from each other, but within clusters and groups, gravity keeps things together, islands of structure in an expanding cosmic ocean. Our galaxy, then, is part of a hierarchy of structures, a member of a group, within a supercluster, within the vast cosmic web that spans the observable universe. We're connected to our neighbors through gravity's invisible threads, part of a community that extends far beyond what our eyes can see. The Milky Way may seem vast and self-contained, but it's really just one neighborhood in a cosmic city that extends farther than we can imagine. Rest in this knowledge of connection, that nothing in the universe exists alone, that everything is part of something larger, woven into the great tapestry of cosmic structure. We've traveled through billions of years, explored structures both vast and tiny. Now let's turn to some of the most intriguing mysteries and wonders that the Milky Way holds, phenomena that challenge our understanding and inspire our imagination. At the very center of our galaxy, surrounding Sagittarius A star, exists a population of stars known as hypervelocity stars. These are stars moving so fast, over 1,000 kilometers per second, that they're escaping the galaxy entirely. They're thought to be created when binary star systems venture too close to the supermassive black hole. One star gets captured while the other is flung outward at tremendous speed, like a stone from a cosmic slingshot. These stellar wanderers will journey through intergalactic space for millions of years, lone travelers between the galaxies. The galaxy contains mysterious objects called gamma-ray bursts, the most energetic explosions in the universe since the Big Bang. When certain massive stars collapse or when neutron stars collide, they can produce focused beams of gamma radiation so intense that if one occurred within a few thousand light-years of Earth, pointing in our direction, it could cause a mass extinction. Fortunately, these events are rare and randomly oriented. For a few seconds, a gamma-ray burst can outshine the combined light of all the stars in the galaxy, a cosmic spotlight of unimaginable power. Throughout the galaxy exist what astronomers call Bok globules, small, dark clouds of dense dust and gas, usually less than a light-year across. They appear as dark spots silhouetted against bright nebulae, like ink drops on luminous paper. These globules are stellar cocoons, places where individual stars or small groups of stars are forming, hidden from view in their dusty nurseries. They were named after astronomer Bart Bok, who first hypothesized in the 1940s that these dark clouds were sites of star formation, a prediction later confirmed. The Milky Way produces cosmic rays, high-energy particles, mostly protons, that zip through space at nearly the speed of light. These particles are accelerated by supernova shockwaves and other violent events, and they permeate the galaxy, constantly bombarding everything, including Earth. Our atmosphere protects us from most of them, but astronauts in space are exposed to this cosmic radiation. Some cosmic rays have energy so high that scientists still don't fully understand what could accelerate them to such extreme speeds. They carry as much energy as a well-thrown baseball, concentrated in a single subatomic particle. Deep within dense molecular clouds exist what astronomers call dense cores, regions where the gas is cold enough and dense enough that molecules can form complex chains. These regions contain organic molecules, including formaldehyde, ethanol, and even amino acids. In essence, the galaxy is a giant chemistry lab, constantly creating complex organic compounds in the darkness between the stars. Every star system that forms inherits this molecular complexity, meaning the building blocks of life are scattered throughout the galaxy, waiting to be incorporated into new worlds. The galaxy contains mysterious X-ray binaries, systems where a normal star orbits a compact object, either a neutron star or a black hole. As matter from the normal star is pulled toward the compact companion, it heats up to millions of degrees, emitting powerful X-rays. These systems can be spectacularly variable, sometimes brightening dramatically over days or weeks as fresh material falls onto the compact object. Some X-ray binaries produce jets, narrow beams of particles shooting outward at a significant fraction of light speed, like cosmic blowtorches extending thousands of light-years into space. Throughout the galactic disk are structures called supershells, enormous cavities in the interstellar medium created by multiple supernovae exploding in the same region over millions of years. These shells can be over 3,000 light-years across and are still expanding, driven by the energy of stellar winds and explosions. They shape the distribution of gas in the galaxy and can trigger new waves of star formation where they compress surrounding clouds. The local bubble that contains our solar system is one such structure. We live inside the cavity created by ancient stellar violence. The galaxy's center contains a mysterious excess of gamma rays that scientists have been studying for years. This signal, dubbed the galactic center GeV excess, might be produced by dark matter particles annihilating each other, or it might come from thousands of rapidly spinning neutron stars called millisecond pulsars. The mystery remains unsolved, a puzzle waiting in the heart of our galaxy. Such mysteries remind us how much we still don't know, that the galaxy continues to surprise us, even after centuries of observation. These wonders, hypervelocity stars, gamma-ray bursts, cosmic rays, complex organic molecules, they're not separate from the story we've been telling. They're part of it, threads woven into the grand tapestry of galactic life. Some we understand, some remain mysterious, but all are part of the rich, complex reality of the Milky Way. The galaxy is not just a collection of stars and gas. It's a living laboratory where the laws of physics play out on scales both vast and tiny, creating phenomena that stretch our understanding and fire our imagination. Drift now through these mysteries. Let them fill your mind with wonder as you relax into sleep, knowing that the universe is stranger and more beautiful than we can fully comprehend. We've explored the galaxy's structure, its motion, its mysteries. Now let's turn to perhaps the most profound question of all: are we alone? What does the Milky Way tell us about the possibility of life beyond Earth? Astronomers estimate that the Milky Way contains between 100 billion and 400 billion stars, and recent observations suggest that nearly every star hosts at least one planet. This means our galaxy likely contains hundreds of billions of planets, a staggering number of potential worlds where life might arise. If even a tiny fraction of these planets harbor life, the galaxy could be teeming with living worlds, each with its own story unfolding under alien skies. Within this vast population of planets, scientists estimate there could be as many as 40 billion Earth-sized planets orbiting in the habitable zones of their stars, the region where temperatures allow liquid water to exist on a planet's surface. These worlds orbit both sun-like stars and the more common red dwarf stars that make up about 70% of the galaxy's stellar population. 40 billion chances for life as we know it, 40 billion potential homes for biology, evolution, perhaps even consciousness. The building blocks of life are remarkably common in the galaxy. Water ice is found throughout the interstellar medium, in comets, on asteroids, and on moons. Organic molecules, including amino acids, the components of proteins, have been detected in molecular clouds, in meteorites, and even on comets. The chemistry of life appears to be written into the basic processes of the galaxy itself. Life may not be an unlikely accident but an expected outcome when the right conditions occur, and those conditions may be far more common than we once thought. The concept of the galactic habitable zone suggests that certain regions of the Milky Way are more conducive to life than others. Too close to the galactic center, and planets face intense radiation, frequent supernova explosions, and gravitational disruptions. Too far out, and there may not be enough heavy elements to form rocky planets. Our solar system sits in a relatively safe, stable region, not too hot, not too cold, just right for long-term planetary stability. But this habitable zone is broad, encompassing perhaps half the galaxy's disk, billions of cubic light-years where life-bearing worlds might exist. The galaxy has been producing potentially habitable planets for a very long time. While Earth is 4.6 billion years old, some planets in the Milky Way could be 8 or even 10 billion years old, orbiting stars formed in the galaxy's earliest generations. If life arose on these ancient worlds at the same rate it did on Earth, some civilizations could have had a 5 billion year head start on us. Imagine civilizations that old. What might they have become? What technologies might they have developed? The mind staggers at the possibilities. Despite the promising numbers, the search for extraterrestrial intelligence has so far yielded silence. The Fermi paradox asks why, if the galaxy should be full of life, we see no evidence of it. Perhaps intelligent life is vanishingly rare. Perhaps civilizations don't last long. Perhaps they're out there but we lack the means to detect them. Or perhaps they're simply very far away, separated from us by vast gulfs of space and time. The galaxy is immense. Even radio signals traveling at light speed would take tens of thousands of years to cross it, and we've only been broadcasting for about a century. In recent years, astronomers have discovered numerous potentially habitable exoplanets relatively nearby in galactic terms. Proxima Centauri b orbits the closest star to our Sun, just 4 light-years away. The TRAPPIST-1 system, 39 light-years distant, contains 7 Earth-sized planets, 3 in the habitable zone. Kepler 452b, nicknamed Earth's cousin, orbits a Sun-like star in the habitable zone about 1,400 light-years away. Each discovery expands our sense of what's possible: rocky worlds, water worlds, planets we never imagined, each potentially harboring its own unique form of life. The search continues through multiple methods. Radio telescopes listen for artificial signals. Optical telescopes search for laser pulses from distant civilizations. Scientists analyze the atmospheres of exoplanets, looking for biosignatures, chemical markers that might indicate life, such as oxygen, methane, or other gases that don't naturally coexist in equilibrium. Each new telescope, each new technique, extends our reach further into the galaxy. Perhaps in our lifetime, we'll detect the first signs of life beyond Earth, a discovery that would fundamentally change our understanding of our place in the galaxy. The question of whether we're alone is really a question about the galaxy itself. Is it a rare garden where life bloomed in just one small corner? Or is it a forest thick with life, where countless stories unfold simultaneously across its vast expanse? We don't yet know the answer. But every day, we learn more. Every discovery brings us closer to understanding whether the Milky Way is our home alone, or a galaxy full of neighbors we've yet to meet. For now, we can rest in the wonder of the question itself, knowing that we live in a galaxy vast enough to contain possibilities beyond our imagination, mysterious enough to keep us searching, beautiful enough to inspire awe. Close your eyes and picture it, a galaxy of billions of worlds, each one unique, each one a story waiting to be told. For all our exploration of the galaxy's vastness, we must remember that we observe it from within, from a single point in a single spiral arm. Our perspective shapes what we see and how we understand it. Let's explore the unique challenges and revelations of studying the Milky Way from inside. When you look up at the night sky, away from city lights, you can see a faint band of light stretching across the heavens. This is the Milky Way itself, the combined glow of billions of stars in the galactic disk, seen edge-on from our position within it. Ancient cultures around the world gave it different names. The Greeks saw it as milk spilled by the goddess Hera, the Chinese called it the Silver River, the Vikings believed it was the path to Valhalla. What all these cultures were seeing, without knowing it, was the inside view of our cosmic home. Because we're embedded in the galactic disk, about halfway out from the center, we can't easily see the Milky Way's overall structure. Dust in the disk blocks visible light, creating dark lanes and obscured regions. The galactic center, though only 26,000 light-years away, is hidden behind vast clouds of dust and gas. Astronomers can only study it using infrared, radio, and X-ray wavelengths that penetrate the obscuring material. It's like trying to understand the layout of a city while standing in a dense fog. You can see what's nearby, but the overall pattern remains hidden. The plane of the Milky Way creates what astronomers call the zone of avoidance, a band across the sky where dust extinction is so severe that distant galaxies beyond our own are difficult or impossible to detect in visible light. About 10 to 20% of the entire sky is affected. This means there are thousands of galaxies hidden from view, concealed behind the veil of our own galaxy's matter. Only in recent decades, with infrared and radio observations, have astronomers begun to map what lies in this hidden zone. The brightest part of the Milky Way in our sky is toward the constellation Sagittarius, where we're looking toward the galactic center through the densest concentration of stars. In contrast, when we look toward the constellation Auriga, we're looking outward toward the galaxy's edge, where stars are sparser and the band of light appears dimmer. This difference helps us orient ourselves within the galactic structure. Our night sky is a map, if you know how to read it, a map drawn in starlight, showing us our place in the cosmic geography. From our vantage point, we've been able to identify and name several nearby stellar nurseries and nebulae. The Orion Nebula, visible to the naked eye as a fuzzy patch in Orion's sword, is the closest large star-forming region at about 1,300 light-years away. The Carina Nebula, visible from the southern hemisphere, is one of the largest and brightest nebulae in the sky, containing some of the most massive stars known. These are our galactic neighbors, close enough to study in detail, teaching us about the processes occurring throughout the galaxy. The Sun's position in the galaxy isn't just favorable for habitability, it's also favorable for astronomy. We're far enough from the center to avoid excessive crowding and radiation, but not so far out that we're in the sparse, metal-poor regions. We're also not in a globular cluster or dense stellar environment where the night sky would be bright with nearby stars. Our relatively quiet location gives us dark skies and a clear view of the distant universe. It's a cosmic coincidence, or perhaps not. Perhaps only in such locations can civilizations develop the technology and curiosity to study the cosmos. Modern surveys have mapped millions of stars in our galactic neighborhood, revealing the three-dimensional structure of nearby space. The Gaia spacecraft, launched by the European Space Agency, has measured the positions and motions of over 1 billion stars with unprecedented precision. This data has revolutionized our understanding of the galaxy's local structure, revealing stellar streams, clusters, and patterns we never knew existed. We're creating a census of our cosmic neighborhood, learning who our neighbors are, where they came from, and where they're going. Despite being inside the galaxy, we've managed to determine its overall structure through careful observation and clever reasoning. By mapping the distribution of young, hot stars in HII regions, by measuring the distances and velocities of gas clouds, by studying globular clusters and variable stars, astronomers have pieced together a picture of the Milky Way's spiral structure, its bar, its warped disk, all without ever leaving our single vantage point. It's detective work on a cosmic scale, using clues scattered throughout the sky to reconstruct a complete picture of something we can never fully see from outside. Our perspective is limited, yes, but it's also intimate. We don't observe the Milky Way as distant outsiders but as participants, as part of the system itself. We're not studying a galaxy, we're studying our galaxy, our home, the cosmic ecosystem that made us possible. Every star you see in the night sky is part of this system. Every constellation, every nebula, every cluster, they're all members of this vast galactic family. And so are you, made of atoms forged in stellar hearts, shaped by billions of years of galactic evolution. Rest now in this belonging, knowing that you are truly a child of the Milky Way, born from its matter, living under its protection, forever part of its ancient story. We've journeyed from the galaxy's birth to the present moment. Now let's drift forward in time, into the distant future, to see what fate awaits the Milky Way in the eons to come. Star formation in the Milky Way is gradually declining. The galaxy is using up its reserves of cold gas, and while some new material arrives from infalling dwarf galaxies in intergalactic space, it's not enough to maintain the current rate. In about 10 billion years, star formation will have slowed to a trickle, and the galaxy will contain mostly long-lived red dwarfs and the cooling remnants of stars that have already died. The age of brilliant star birth, which has lasted for over 13 billion years, will eventually come to a quiet close. In approximately 4 billion years, the Milky Way and Andromeda will begin their collision. Despite containing hundreds of billions of stars between them, actual stellar collisions will be extremely rare because stars are so small compared to the vast distances between them. Instead, the two galaxies will pass through each other like ghosts, their shapes distorted by gravitational interactions, creating long tidal tails of stars streaming into intergalactic space. From Earth, if anyone is still here to see it, the night sky will transform. Andromeda will grow larger and larger, eventually filling half the sky with its spiral magnificence. After the first pass-through, the two galaxies won't simply separate. Gravity will pull them back together for a second collision, and then a third. Over the course of about 2 billion years, the multiple encounters will scramble the ordered spiral structures of both galaxies. Stars will be flung into vast orbits, some escaping into intergalactic space, while others settle into new configurations. Eventually, approximately 6 billion years from now, the merger will be complete. The result of this merger will be a single elliptical galaxy, a vast, football-shaped collection of stars with no spiral arms, no distinct disk, just a smooth distribution of stellar orbits in all directions. The two supermassive black holes at the centers of the Milky Way and Andromeda will also merge, creating a single behemoth black hole with a mass of over 100 million suns. This merger will release tremendous energy in the form of gravitational waves. The new galaxy might be called Milkomeda, or perhaps some future civilization will give it a name we cannot imagine. Our solar system will likely survive this galactic collision, though its position within the new merged galaxy will change. We might be flung into the outer halo, becoming a halo star orbiting far from the new galactic center. Or we might remain in the inner regions. Either way, the familiar constellations will be completely rearranged, and the night sky of Earth, if Earth still exists, will be utterly transformed. By this time, our Sun will be near the end of its main sequence life, beginning its transformation into a red giant. Approximately 7.5 billion years from now, our Sun will exhaust the hydrogen in its core and begin fusing hydrogen in a shell around an inert helium core. This will cause it to expand dramatically, becoming a red giant star. It will grow so large that it will likely engulf Mercury and Venus, and possibly Earth as well. Even if Earth's orbit somehow survives, the intense heat will boil away our oceans and atmosphere, rendering the planet uninhabitable long before. The Earth that nurtured life for billions of years will finally meet its end, not with a bang, but with the dying gasp of its parent star. After the red giant phase, the Sun will shed its outer layers, creating a beautiful planetary nebula, and its core will collapse to become a white dwarf, a dense, Earth-sized ember slowly cooling over trillions of years. The planets, or whatever remains of them, will continue to orbit this stellar remnant in the darkness, illuminated only by the fading glow of the white dwarf and the light of other stars in the merged galaxy. This is the fate of most Sun-like stars, a slow fade into darkness, their light diminishing over incomprehensible spans of time. Looking much farther ahead, trillions of years into the future, star formation throughout the merged galaxy will cease entirely. All the gas will have been used up or expelled. The galaxy will enter what astronomers call the degenerate era, a time when only stellar remnants remain. White dwarfs will slowly cool to black dwarfs. Neutron stars will continue their silent vigil. Black holes will be the most dramatic objects, occasionally flaring to life when they capture passing matter. Eventually, even the galaxy itself may dissipate, stars gradually ejected by gravitational interactions over countless eons, until nothing remains but isolated stellar remnants drifting through the dark. But this future is so distant, trillions upon trillions of years away, that it's almost beyond comprehension. Between now and then, so much time will pass that we cannot imagine what might occur. Perhaps other civilizations will arise. Perhaps they'll master technologies we can't conceive of. Perhaps they'll find ways to preserve themselves, to migrate between galaxies, to outlast the death of stars. Or perhaps not. Perhaps we, and any other consciousness that arises, are brief flowers blooming in the cosmic spring, destined to fade when the long cosmic winter arrives. But that winter is unimaginably far away. For now, and for billions of years to come, the galaxy remains vibrant, alive, full of possibility. Rest in the present moment, knowing that the future is vast and uncertain, but for now, for this moment, you exist under the light of living stars in a galaxy still young and vital. Let time stretch out before you like an infinite road, and let yourself drift into peaceful sleep, cradled by the slow rhythms of cosmic time. We've traveled through time and space, explored structures and mysteries. Now, as we near the end of our journey, let's reflect on something profound, the connection between the galaxy and us, between the vast cosmic processes we've explored in the brief, beautiful phenomenon of human consciousness. Every atom in your body was created in the galaxy. The hydrogen formed in the Big Bang moments after the universe began. The carbon, nitrogen, and oxygen that make up most of your mass were forged in the nuclear furnaces of stars over billions of years. The iron in your blood was created in the violent explosion of a supernova. You are, quite literally, made of stardust, the galaxy's matter rearranged into temporary patterns that can think, feel, and wonder. This isn't poetry, it's scientific fact. We are the galaxy becoming conscious of itself. The formation of our solar system was influenced by a nearby supernova. Scientists believe that the shockwave from an exploding star compressed the cloud of gas and dust that would become our sun and planets, triggering its collapse. Isotope evidence in ancient meteorites suggests this supernova occurred just before or during the solar system's formation. Without that cosmic violence, we might not exist. Death and birth are intimately connected in the galaxy. One star's ending creates the possibility for new worlds, new life. Humanity has existed for only about 300,000 years, a mere blink in the galaxy's 13 billion-year history. If we compress the galaxy's entire history into a single year, with the Big Bang occurring on January 1st, our solar system wouldn't form until early September. Life on Earth wouldn't appear until late September. Dinosaurs would walk the Earth for a few hours on December 30th. All of human civilization, from the first cities to the present day, would occupy only the last few seconds before midnight on December 31st. We are newcomers to this ancient story, late arrivals to a party billions of years in the making. Despite our brief existence, humans are the only known species in the galaxy that can contemplate the galaxy itself. We've built telescopes to see across cosmic distances. We've developed theories to understand how stars form and die. We've sent spacecraft beyond our solar system carrying messages to anyone who might find them. In the vastness of the Milky Way, we may be the only consciousness currently asking these questions, seeking these answers. Or perhaps we're one of many, but either way, our ability to understand, to wonder, is remarkable. The elements essential for human technology were all created in the galaxy over billions of years. Silicon for our computer chips came from dying stars. The rare earth elements in our smartphones were created in neutron star collisions. Gold and platinum formed in the same violent mergers. Our entire technological civilization depends on the galaxy's long history of stellar nucleosynthesis. The periodic table is a record of cosmic processes. When you hold a smartphone, you're holding fragments of exploded stars and colliding neutron stars, shaped by human ingenuity. Humans are the first known species on Earth to understand our cosmic address. We know we're on the third planet from a yellow dwarf star, in the Orion Spur, about 26,000 light-years from the galactic center, in a barred spiral galaxy containing hundreds of billions of stars, part of the local group, within the Virgo supercluster. This knowledge is less than a century old. Our great-grandparents didn't know these things. We've gone from thinking Earth was the center of everything to understanding our true place in the cosmic architecture in just a few generations. The galaxy has shaped human culture in countless ways. Before light pollution, Every human culture could see the Milky Way stretching across the night sky, and it featured in their myths, their navigation, their sense of cosmic wonder. The ancient Greeks, Polynesians, Aboriginal Australians, Native Americans, Chinese, Indians, all developed stories to explain that luminous band. Those stories connected people to something larger than themselves, something eternal and mysterious. In our modern world, many people never see the Milky Way due to city lights. We've lost a connection that was once universal to human experience. In 1977, humanity launched the Voyager spacecraft, each carrying a golden record, a time capsule containing sounds and images from Earth, meant for any extraterrestrial intelligence that might encounter them. These spacecraft are now in interstellar space, the first human-made objects to leave the solar system. They'll drift through the galaxy for millions or billions of years, long after humanity is gone, carrying our message to the stars. It's an act of cosmic optimism, sending a greeting into the vast darkness, hoping someone, someday, somewhere, might find it and know we existed. The relationship between humanity and the galaxy is paradoxical. We're infinitesimally small, brief sparks of consciousness on a tiny world orbiting an ordinary star. Yet we're also observers, understanders, meaning makers. The galaxy doesn't know it exists, but through us, it knows itself. Perhaps this is our purpose, if purpose is even the right word, to be the part of the universe that can look back at itself with wonder. To be the galaxy's way of experiencing beauty, of asking questions, of seeking truth. You are part of this. Your consciousness, your ability to contemplate these vast scales and times, is one of the most remarkable phenomena the galaxy has produced. You are star stuff pondering stars, atoms contemplating atoms, the cosmos reflecting on its own existence. Rest now in this knowledge, that you belong to something vast and ancient, that you're connected to everything through the matter you're made of and the processes that created it. Close your eyes and feel that connection, to the stars, to the galaxy, to the universe itself. We've journeyed through 13 billion years, explored structures spanning hundreds of thousands of light years, and contemplated mysteries that challenge our understanding. Now, as our story draws to a close, let's reflect on a few final wonders, and on what it all means. The Milky Way is just one galaxy among an estimated 2 trillion galaxies in the observable universe. Each of those galaxies contains billions or trillions of stars. The number of stars in the universe likely exceeds the number of grains of sand on all of Earth's beaches. And yet, despite this incomprehensible vastness, our galaxy is special to us, because it's ours. It's the only galaxy we can study in intimate detail, the only one whose individual stars we can see with our naked eyes, the only one we can truly call home. In all that cosmic immensity, the Milky Way is our address, our neighborhood, our context for existence. The light we see from distant parts of the galaxy is ancient. When you look at a star 10,000 light-years away, you're seeing it as it was 10,000 years ago, before human civilization, before agriculture, when our ancestors were still hunter-gatherers. The light from the galactic center left on its journey 26,000 years ago, during the last ice age. We don't see the galaxy as it is now, We see a tapestry woven from light of many different ages, a history book written in starlight. Time and space are intimately connected. To look far away is to look back in time, to see the galaxy's past while living in its present. Despite everything we've learned about the galaxy, its structure, its history, its contents, it remains fundamentally mysterious. We don't fully understand dark matter, which makes up most of its mass. We don't know if life exists elsewhere within it. We can't predict exactly how its merger with Andromeda will unfold. We're still discovering new structures, new phenomena, new questions. The galaxy continues to surprise us, teaching us humility even as it reveals its secrets. The more we learn, the more we realize how much we don't know, and perhaps that's exactly as it should be. And so our journey through the galaxy comes to an end, though really, it never ends. The galaxy continues its ancient dance, rotating through space, creating new stars, recycling old matter, evolving slowly toward a future we can barely imagine. Everything we've explored tonight is real, happening right now all around us. Stars are being born in cold molecular clouds. Others are dying in spectacular supernovae. Planets orbit countless suns. Gas streams between galaxies. The supermassive black hole at the center quietly accretes matter. The galaxy merges slowly with smaller companions while approaching its eventual collision with Andromeda. All of this unfolds on timescales so vast that to our human perception, the galaxy seems eternal and unchanging. But it's not. It's a dynamic, living system, constantly in flux, never the same from one moment to the next. And you are part of it. Not separate from it, observing from outside, but woven into its very fabric. The calcium in your bones was created in a dying star billions of years ago. The oxygen you breathe was forged in stellar fusion. The water in your cells has been recycled through countless forms over the galaxy's history, perhaps once part of a comet, or a molecular cloud, or another living being on another world. You are a temporary arrangement of the galaxy's matter, borrowed for a brief time, animated by energy, conscious and aware. One day, those atoms will return to the cosmic cycle, perhaps to be incorporated into new stars, new worlds, new forms we cannot imagine. But for now, in this moment, you exist. You can think, feel, wonder, dream. You can contemplate the vastness of space and time. You can feel awe at the beauty of it all. The galaxy has been building toward this moment for 13 billion years, creating the elements, forming the stars, shaping the structures, all the cosmic processes that eventually led to you, here, now, able to hear this story and understand it. That's not mystical thinking, it's simply the truth of causation traced backwards through time. The galaxy made you possible. And in return, through you, it knows itself. So rest now, knowing that you are exactly where you belong, in a spiral arm of an ancient galaxy, on a small blue world orbiting a yellow star, under the protection of countless suns, part of a story so vast and old and beautiful that we can barely comprehend it. The galaxy holds you gently in its gravitational embrace. The same force that shapes stars and moves worlds also keeps you safely on Earth's surface. You are held, you are home, You are part of something infinitely larger than yourself, yet intimately connected to you. Let this knowledge bring you peace. Let the vastness of space and time remind you that your worries are small and temporary. Let the beauty of the cosmos fill you with wonder. Let the eternal cycles of creation and destruction remind you that change is natural, that endings lead to new beginnings. Close your eyes now, and picture the galaxy in your mind. See the spiral arms glowing with young stars. See the ancient globular clusters in their patient orbits. See the dark lanes of dust where new stars are forming. See the central bulge glowing golden with ancient light. See yourself on Earth, under the night sky, part of this magnificent structure. You are made of stars. You are the galaxy's child. You are a brief, beautiful moment of consciousness in the cosmic night. And now, rest. Let sleep take you gently. Let your mind drift through the stellar spaces we've explored tonight. Let yourself float peacefully through the cosmic dark, knowing you are safe, you are home, you are exactly where you should be. The galaxy has been here for billions of years. It will be here billions more. And for this brief moment, you are alive within it, conscious within it, able to appreciate its beauty. That is enough. That is everything. Sleep well, child of the stars. Sleep well, under the light of the Milky Way.